Hi guys, this is Chemistry 9701, paper 42, May-June 2022. So number 1, 1A, the solubility of the group 2 hydroxides increases down the group. Explain this trend. This is a 3-mark question, and usually the other question that A-level likes to ask is explain why the solubility of group 2 sulfates decrease down the group, and it's practically the opposite of answering a question on group 2 hydroxides. So for this, why group 2 hydroxide solubility increases down the group is because the enthalpy change of lattice and enthalpy change of hydration both becomes less negative or less exothermic. And so the delta H lattice changes more than the delta H of hydration. So changes more means that the enthalpy change of lattice becomes more or less negative than the enthalpy change of hydration. And therefore, the enthalpy change of solution becomes more negative or more exothermic, increasing its solubility of group 2 hydroxides. For group 2 sulfates, it's practically the same. Both of them decrease, but one of the lattice or the enthalpy change of hydration decreases more than the other, which affects the enthalpy change of solution. So B, the solubility of BeOH2 or beryllium hydroxide in water is 2.4 times 10 power negative 6 gram per dm cube. Later, we would see that X solubility is 2.4 times 10 power negative 6 gram per dm cube. We have to take note that it is in grams. Okay, at RTP. I write an expression for the solubility product KSP of beryllium hydroxide and state its units. So the first thing you have to do in these types of questions is to form an equation of the dissociation of beryllium hydroxide in water. So it forms Be2 plus ions and 2OH minus when balanced. So we usually don't write the solid compound in the KSP because the solid has a constant concentration, and so we only write the ionic. Then because it has a coefficient of 2, we write the power of 2, and because it's practically x multiplied by x square, it forms x cubed. So mole per dm cube, we cube it, we form mole cube dm negative 9. I calculate the numerical value of KSP for BeOH2 at 298 K, which is at room temperature and pressure. So first thing you have to do is to convert gram to mole. In a formula of mole is equals to mass over mR, you rearrange it. So because the mR of BeOH2 is 43, the mass is 2. This is assumed to be in 1 dm cube. There is 2.4 times 10 power negative 6 grams of BeOH2. So in 1 dm cube is equal to how many moles? So you divide this by the mR to form this 5.581 times 10 power negative 6 mole per dm cube. So this is assumed to be the new value of the X or the solubility. So KSP, we use this formula X because Be2 plus, and then times 2x because 2OH minus, and then you square it. We get 4, 2 power 2, 4, x squared times x is equal to 4x cubed. So 4 multiplied by the new x, you insert, don't forget the cube, we get this, and therefore the KSP is 6.95 times 10 power negative 22 when 3 significant figures. C. BeOH2 is soluble in aqueous solutions containing an excess of hydroxide ions and forms the complex ion BeOH42-. This complex ion has similar shape to that of CuCl42-. So this is going to be of help later. So Ci, define the term complex ion. So complex ion is a molecule or ion formed by a central metal atom or ion and surrounded by one or more ligands. Ligands is species that has one or more lone pair of electrons that can form dative bonds to the central metal atom or ion. So this is an example of complex ion. This is complex ion, complex ion. Draw a three-dimensional diagram to show the structure of the complex ion BeOH4 2 minus. Name the shape of BeOH4 2 minus because the OH, there's 4 of them. So it's a tetrahedral structure with a 3D structure. So you have to shade this, you have to make this line to show that it is in front, this is in front, but this is at the left back of BE. It's a 3D structure. And don't forget the charge, OH, and remember the bond is bonded to the O, not the H. So it is tetrahedral. Okay, next question. DI. Explain what transition elements can form complex ions. So this question very oftenly comes out in A level, especially in the recent papers. They could come in 2 or 3 marks, but in here it's only 1 mark. So you could say transition elements have incomplete d orbitals. That's always the first thing that you have to answer. And therefore, they can form a dative bond by accepting lone pair from ligands. This is the main thing that you have to answer though. Next, II. Complete table at 1.1 to show the coordination number of each metal ion and the shapes and overall polarities of the complex ions listed. So we know that because it is a square planar, so PT is bonded to this compound actually has 2 coordinations. So it's gonna be like this, Cl, Cl, and then this, for example, is going to be bonded like this. It's going to be and therefore the coordination number is 4, and it is a polar compound. It's a polar compound because it is not symmetrical actually. Okay, next. AgNH3 2+, linear. It is linear in shape because Ag bonded to NH3 bonded to NH3, and then minus, it's linear with a coordination of 2 because 2 bonds, and then it is non-polar, so it's symmetrical. So FeC2O4 3 minus is actually octahedral because this is going to form, this Fe is going to be form this to this, and then 2 bonds here to here, and then 2 bonds here to, 2 bonds here and here. So total coordination number is 6, 1, 2, 3, 4, 5, 6, and it's non-polar because it is going to be symmetrical. Next, define the stability constant. Oh, and also this is polar because it's actually not going to be symmetrical, and there is like this. If the N is bonded to here, there's no way this compound is going to be symmetrical. So EI, define stability constant K-step. So K-step is actually the equilibrium constant for the formation of a complex ion in a solvent from its constituent molecules. So II, nickel can form complexes with the ligands En, H2NC, H2CH2, and H2, and in this compound as shown. Okay, construct an expression for the stability constant for equilibrium 1. So this is the equation. We have to insert all of them, and usually always constants are always products over reactants, and this is the products over reactants. And then because this has a coefficient of 3, you power 3, and so the units is x over x cubed is equals to x over x4 is equals to 1 over x cubed, so x power negative 3. So mole dm cube, I'm gonna power by negative 3, like here. And then it becomes mole power negative 3, dm power negative 9. And this is the units. I. Describe what the K-step values indicate about the position of equilibrium for equilibrium 1 and 2. Use the K-step values to deduce which complex this or this is more stable. So K-step is higher in equilibrium 1 than equilibrium 2. Is higher in equilibrium 1 than equilibrium 2. And so because K-step is proportional to the products is higher. So equilibrium lies to the right and more to the right for equilibrium 1. So NiEN32 plus is more stable because the equilibrium moves to the right and less of this compound dissociates back into this. So higher K-step is equal to higher stability, so not shifting. So because for this equilibrium 2, it has a lower K-step, and so lower products are produced, so the equilibrium lies to the left. And so more of this dissociates, and because this is less stable. And so the answer is K-step is higher so the answer is it is more stable NiEN2 plus, which is the product of equilibrium 1. 2a. Explain why transition elements have variable oxidation states. It is because the D and S subshells are similar in energy, and therefore it causes incomplete d orbital and so it causes variable oxidation states. So sketch the shape of a 3D XY orbital. So this is actually memorizing, where it's a 3D structure. From the top view, it's actually like this. Like this from the top view, but then this is a 3D view, so this is actually towards the back of this vertical line. So this is how you would draw it. That's why this is actually looks like it's in the middle of Z when it's not. None of the orbitals actually cut the axes. So C, explain why transition elements form colored compounds. So transition elements form colored compounds. This actually memorization, 3 marks, similar to what the question before asked. Transition metals have incomplete d orbitals. That's one, that can split into 2 sets of orbitals. So 2 sets of orbitals, one is higher orbital, one is lower orbital. So electron then absorbs light energy to move to a higher energy level, and it gets excited. And then this difference in energy level, higher and lower, causes when the light is absorbed, it corresponds to a specific wavelength of a color. Or you could say, in other words, the light absorbs a color and the complementary color is observed. So the color seen is complementary. The color seen is complementary to the color of the one that is absorbed. So, for example, if the element is to absorb the color red or the color green, let's say, absorb the color green, the color that it would show could, if, for example, let's use the example of plants. If plants are green, they have a green color that is observed color green, and because of this actually red and blue light are absorbed, and red and blue are complementary colors to green, and therefore you could say that the color seen is complementary color to the one absorbed. So D, aqueous solutions of copper salts contain CuH2O62 plus ions. Equilibrium 3 and equilibrium 4 show the 2 reactions of these ions, this and this. State the color of CuOH2S and CuNH3 for H2O2 plus. And this is actually memorization from I'm going to insert a Christmas tree here. So we're gonna see that CuOH2 actually has a pale blue color. CuNH3 for H2O2 plus is actually deep blue, and they could have a precipitate texture or just an aqueous solution. For example, this S is, so it's precipitate. And this is actually solution, deep blue solution. Okay, II. Use Le Chatelier's principle to explain why precipitate form when NaOH is added dropwise to CuH2O6 2+. So NaOH, when added, causes a higher OH minus concentration, which causes the equilibrium to shift to the right. So CuH2O6 2+ is this. So when NaOH is added, it increases the OH minus concentration, and so the equilibrium shifts to the right to balance out the increase in the OH minus. So you want to make it equal, both sides equal. So we want to decrease and use up the OH minus ion. So the yield, so this yield increases and this decreases. So because this is actually a solid, that's why a precipitate is formed. Okay, E. There are two possible stereoisomers with the formula CuNH3 4H2O2 2+. Draw three-dimensional diagrams to show the two isomers. So two stereoisomers. So in here we can actually know that there is going to be cis and trans isomers, which are both geometrical isomers, where this H2O and H2O side by side. So it is cis isomerism, and H2 and H2O, remember that the bond is attached to the O, so, and not the H, and so this is trans isomerism. And don't forget to draw the 3D structure with this shaded and this dotted lines. Don't forget the charge also to the whole thing, 2+. Okay, next question. 3AI. Define first electron affinity. First electron affinity is the enthalpy change of 1 mole of electrons, or the enthalpy change gained by 1 mole of gaseous atoms. So the first electron affinity of an atom is usually an exothermic process, whereas the second electron affinity is an endothermic process. This question comes out often, and you should really memorize the answer to this. So it is because energy is required to overcome the first repulsion between the electron and the anion, which are both negatively charged, and this requires more energy, and therefore it's exothermic process. There's the difference with the first electron affinity is exothermic, and the repulsion is going to cause more heat to be released. Describe the general trend in the first electron affinities for Cl, Br, and I. Explain your answer. So down the group, the first electron affinities become less negative or less exothermic. Because down the group, increase in shielding effect or distance causes weaker attraction between the nucleus. So increase in size, weaker attraction between the nucleus and the incoming electron, and therefore less energy is released. So next is drawing an entire diagram, but we need to calculate the first electron affinity for iodine. Use relevant data from table 3.1 in your working, and it may be helpful to draw a labeled energy cycle. So this energy cycle usually has a base which starts with CnI2 solid for this question. In this case, because the main product, the zinc iodine solid. So zinc iodine 2S. The first thing that forms this is enthalpy change of formation, which goes downwards. First is enthalpy change of formation. Let's use color. Enthalpy change of formation, standard enthalpy change of formation of zinc is -208. So enthalpy change of formation is negative 208. Next is going up is atomization of zinc from solid to gas. So atomization is at standard enthalpy change of atomization of zinc, which is solid to gas. Standard atomization. This standard atomization. Let's do it like this. Okay. Okay, next is zinc that is gas is going to lose 2 electrons in a process called first and second ionization. So the first ionization energy of zinc is 906. Second ionization energy of zinc is 1733. You can draw two times. So zinc gas plus blah 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 is going to form zinc plus gas plus E minus plus blah blah blah, and then zinc 2 plus gas plus 2E plus another E minus actually plus da, da, da. So it's one by one, first ionization energy, second ionization energy. However, in here I combine immediately first and second ionization energy, therefore it's this. Next is the enthalpy change of iodine from solid to gas. So enthalpy change of sublimation of iodine. So this enthalpy change of sublimation. Enthalpy change of sublimation of iodine is 62. This table can actually help you a lot because it's solid to gas, it states here. And sometimes this table often messes with you. It says II bond energy 151 when this is actually really not needed at all. So ignore this. Okay, next we got because I2, we actually need to convert it to I actually. Oh, I forgot about this. This is actually, so the I bond energy is actually required. So bond energy is required. So we need to write 151 also here. Sorry. And then it's going to convert to here, and then this is actually going to form zinc 2 plus and 2I gas, which would then undergoes lattice energy of zinc iodide to form zinc iodide at negative 20605. So lattice energy. Okay, so first electron affinity is something that you want to find. Azure gray. This is what you want to find. It always undergoes first electron affinity. And so when we combine everything here, this is equal to this entire thing. So negative 208 is equals to, you add up 131 plus 2639 plus 62 plus 151 plus 2EA electron affinity minus 2605 or plus negative 2605. So EA, I would get negative 293. Why this is 2 is because there are 2 electrons, and so I want to get rid of the 2 electrons. I divided by 2 later. Negative 293 I got. That's the answer that I got. And next C. So predict how the enthalpy change of lattice of CdI2 solid differs from the enthalpy change of lattice of zinc I2 solid. So place a tick in the appropriate box in table 3.2. So I have placed the tick in enthalpy change of lattice of CdI2 is less negative. Less negative means more positive, means a larger value of lattice energy is required in CdI2 than zinc I2. Okay. Larger lattice energy. So explain your answer. This is because CD2 plus is a larger atomic size, so less charge density. Charge density is actually charge density is equals to charge over mass. So because CD2 plus is larger atomic size means that it is heavier. Heavier means indirectly proportional to the charge density, means there is less charge density, and therefore there is less nuclear attraction between the ions. Less weaker nuclear attraction between the ions means that it requires a greater amount of energy to put the ions together and to form from gas to a lattice. In order for the particles to be much closer together, it requires far greater energy in for CdI2 molecules than the zinc I2 molecules, and therefore less negative. Okay, next question. 4a. Calcium carbonate decomposes on heating. CaCO3 solid becomes CaO plus CO2 gas. Table 4.1 shows the values of Gibbs free energy change. Gibbs free energy change, that's the symbol for this reaction at various temperatures. Assume the standard enthalpy change delta H and the standard entropy change for this reaction remain constant over the temperature range. Use the data in table 4.1 to plot a graph. So here I've plotted a graph of this starting at 1050. 1050 is around here, 9.9 is around here. This is the first plot point, and I continue to plot and I form this line. Okay, I calculate the gradient of your graph, determine. So in order to calculate the gradient of a graph, I actually use this data rather than taking points in here, which is much more difficult. So I y2 minus y1 over x2 minus x1. That's the formula for gradient. 9.1 minus 4.3 times 10 power 3, because k, kilo, over 1050 minus 1085, I get negative in brackets, negative 160, and this is no kilos, so that's why I put times 10 power 3 here. Don't forget that, that's actually important. Okay, next question. B. Group 1 hydrogen carbonates MHCO3 decompose on gentle heating to give a corresponding metal carbonate carbon dioxide water vapor. So this question have itself told you the products of the reaction. So write an ionic equation for the decomposition of the hydrogen carbonate ion. So it says ion. So MHCO3, you have to split it into two. It has M1 hydrogen carbonate. M1. I mean group 1. So it states that M is actually a compound from group 1, which group 1s have a charge of +1. So MHCO3 is M plus NHCO3 minus. So HCO3 minus, I don't need to write the one actually there, forms metal carbonate M2CO3, which I have split into M2 plus and CO3 2 minus. So I only write CO3 2 minus plus carbon dioxide plus H2O. Okay, the thermal stability of group 1 hydrogen carbonates increases down the group. Suggest the explanation for the trend in thermal stability for the group 1 hydrogen carbonates. Besides solubility of group 2 compounds, we also have a trend in group 1 hydrogen carbonates, which involves down the group, the size of cation has to be cation, or group 1 metal actually increases. It actually increases, and the H plus size, ionic size, actually stays constant, like here. The polarizing power decreases of HCO3 minus. Because why it decreases? Because in Li plus, the polarizing power is actually like this. It requires high polarization, so high distortion. But as you go down, the size almost becomes the same, and therefore less distortion occurs in and the lowest element of group 1, and therefore it has the strongest bond, and you could say less weakening of the CO bond, and therefore this is the most thermally stable because the bond is the most thermally stable because the bond is strong bond. Okay, this is how it would look like. CO, this distortion occurs here and it's easily broken. Okay, C, the buffer system in seawater contains a mixture of HCO3 minus and H2CO3. Equilibrium 5, this is the equation. Define a buffer solution. A buffer solution is a solution that resists or opposes the change in pH when small amount of acid or alkali is added. So you could say that a buffer solution is a solution that opposes change in pH. So whenever an acid or a small amount of acid or a small amount of alkali is added, the buffer pH stays constant unless it reaches the maximum amount of acid or alkali in the solution. So in II, construct two equations to show how equilibrium 5 acts as a buffer solution. So you could actually do it. The two equations consist of a buffer solution reacting with an acid and a buffer solution reacting with an alkali. So when the buffer solution, mixture of HCO3 minus and H2CO3, reacts with an acid, the H plus will react with HOC3 minus, which of course is the opposite of H plus, and the H will move here. H will move here to form H2CO3, and then with an alkali, OH minus, the H extra H will move here to neutralize and form H2O and HCO3 minus, and therefore the pH is maintained. So for III, the HCO3 minus to H2CO3 ratio in a sample of seawater is 14.1. So in this equation, we should calculate the pH of the sample. pKa of H2CO3 is 6.35. So there are two methods in answering this question. I prefer to do method number 1, but you could also do method number 2, which is, if I'm not mistaken, is the method that they use in the answer key. So pH is equals to pKa plus logs of salt concentration over acid concentration, and this is in a ratio. So because this is concentration of HCO3 minus to H2CO3 is 14.1 to 1 ratio, I inserted it here. And the pKa is already mentioned here, 6.35. So just simply put in the equation and you get pH 7.5. Or method 2, you could use the long way using the reaction. So first you need to form Ka, constant. The constants express the equation in a constant. So in order to express it in the express the constant in an expression, we have to do products over reactants, and because H2O is always a constant concentration, we ignore the H2O that is supposed to be here. I cross it out, and therefore I get this expression, which is equal to 14.1 Ka, if I'm not mistaken. Okay, then I don't think it's equal to 14.1 actually. Okay, let's focus next. pKa is equals to, we use a formula negative log Ka. pKa is 6.35, we insert, and then we find for Ka with 4.4 is 668 times 10 power negative 7, and because the concentration here 14.1 over 1, this actually equals to 14.1. So Ka 4.4668 times 10 power negative 7 is equal to is equal to Ka, which is equal to, is equal to the acid multiplied by the ratio of the concentration multiplied by the ratio, which is equal to 14.1, and we arrange it to get 3.167 times 10 power negative 8. And wait, this is only the concentration of H plus. We insert in another formula, pH equals to negative log H plus is equal to 7.5. Yeah, okay. Next, 5a. Complete table 5.1 to predict substance liberated at each electrode during electrolysis of the indicated electrolyte with inert electrodes. So, PtBr2L, the substance liberated at the anode, substance liberated at the cathode. Next, so the first one, the one liberated in the anode, which is the negative electrode, cathode is the positive electrode. The substance liberated is Br2. The substance liberated in the cathode is Pb. Next is concentrated NaCl, Na+. So aqueous, right? So there is of course H plus and OH minus. And because H plus has a higher reactivity, the one liberated in the cathode is H2. And the one liberated in the anode is Cl2 because it is a Cl minus. CuNO3 2. Aqueous, again, there's H plus and OH minus, and because OH minus will form O2, O2 is liberated at the anode, and Cu is liberated at the cathode, Cu solid. And so B, an electrolytic cell is set up to determine a value for the Avogadro constant L. The electrolyte is dilute sulfuric acid and both electrodes are copper. When a current of 0.6 A is passed through the acid for 30 minutes, this is required for later information, the anode decreases in mass by 0.350 grams. So state the relationship between Faraday constant F and the Avogadro constant L. This is by memorizing, it has a relationship of L. F equals to L multiplied by E. And so, this is tricky, rather tricky. Use an experimental information in B and data from the table on page 23 to calculate a value for the Avogadro constant L. Show all your working. So the first thing you have to do is to calculate for the Cu2 plus mole form with the formula of mole is equals to mass over mR. The mass is known here to be 0.35. The anode decreases in mass by 0.35 grams, means that that is the mass of Cu solid that is already formed. Divided by the mR of Cu is 63.5, so there is mole 5.5118 times 10 power negative 3 moles of Cu formed. So next we use the known data, I and T. From that, we can use the equation Q equals to IT. So charge is equals to current times time, 0.6 I, multiplied by 30 minutes. 30 times 1 minute has 60 seconds. So the T is always in terms of second. So we get charge of 108T. So in a total charge of 108T, and each electron has a mass of each charge has a charge of 1.6 times 10 power negative 19. How many is the total number of electrons? So total number of electrons is the total charge divided by the charge of one particle. So we get 6.75 times 10 power 21 number of electrons present. So the total number of Cu2 plus ions present is actually divided by 2 because of the charge. For every Cu2 plus ion, there's actually twice the number of charges. So divided by 2, so equals to 3.75 times 10 power 21 total Cu2 plus ions formed. So number of Cu2 plus per mole. So 1 mole, we use the formula F over E. So L is equals to F over E. We rearrange from the answer in here. So F is 3.7375 times 10 power 21 divided by 5.5118 times 10 power negative 3. We get 6.12 times 10 power 23, and therefore that's the Avogadro constant, 6.12 times 10 power 23. See, this is the charge. This is a charge of 1 electron, 1.6 times 10 power negative 19. 2 electrons is lost per Cu2 plus ion. So 6a, the region and conditions required for the nitration of benzene, benzoic acid, and phenol are shown in table 6.1. Compound benzene, benzoic acid, phenol, and regions and conditions for nitration. Concentrated HNO3 reacted with concentrated H2SO4 to generate electrophile NO2+. Complete figure 6.1 to show the mechanism of the reaction between benzene and NO2+. So include all relevant curly arrows and charges. So when the electron goes there, it forms a bond, and so H plus from the bond forms here, and therefore forms NO2 plus H plus. Next, for CAII, write an equation to show how H2SO4 is regenerated. So H2SO4 is actually regenerated from HSO4 minus plus H plus forms H2SO4. Okay, so draw the major products from the mononitration of benzoic acid and of phenol. So major product of benzoic acid is benzene, benzoic acid, and NO2 in position number 3. Major product from phenol is position 2 and position 4. Okay. And so C, compare the relative ease of nitration of benzene, benzoic acid, phenol. Explain your reasoning, include reference to the structures of the 3 compounds in your answer. So phenol has the relative is the most easiest to conduct nitration because phenol has a lone pair of oxygen that overlaps or delocalizes the benzene ring. So if we are to draw it, it would be phenol OH bond delocalizes into the benzene ring. The phenol accepts the electrophiles better. So next, let's immediately skip to benzoic acid. Why it is the least easiest to nitrate to conduct nitration in. So benzoic acid, COOH. The CO bond in COOH is electron withdrawing group, and therefore it decreases the electron density in the ring. So less electrons is present in the ring as compared to benzene, and therefore it is more difficult for the compound to accept NO2 plus ions. So this is the least easiest to for nitration to occur in benzoic acid. So D, the azo compound Congo red is used as an acid-base indicator and can be made by the route shown in figure 6.2. In step 3 of the synthesis, compound Y reacts with compound Z, and compound Z is made from compound X. Wow. And assume that negative SO3 minus Na plus groups do not react. So first I need to form this, the clue already. I need to know that there is 2 and 2. And so C6H5, I form the same thing, but because the O disappears and there's only 1, 2, 3, 4 times 2, 8H, there's supposed to be only H8. However, there are 4 more H atoms, and so I know that NH2 has formed in either side, and this is the compound. So in step 2, each of these NH2 forms into N triple bond N with a plus atom in the first nitrogen atom in each side. And so I know that this is this, and there are 2 compounds of the same. So this is the same compounds. So I need to form, this is equal to this. So it is actually a compound, if with 2 benzene rings, is actually called naphthalene. with NH2 here and with SO3 minus Na plus here, and therefore it's going to form bond later here with the N triple bond N. I suggest structures for XYZ and draw them in the boxes as I've shown here. Give the regions and conditions for step 1 and step 2. For step 1, reduction. Step 1, hot, thin, have to be hot or with heat, plus concentrated HCl followed by NaOH. Answer key, I think, if I'm not mistaken, doesn't say followed by NaOH, but it's recommended that you state followed by alkaline conditions. Then step 2, HNO2 react with HCl at 10 degrees Celsius or less than that, to prevent any mixture of products, or you could say NaNO2 plus HCl at 10 degrees Celsius. Okay, next question. State the uses of TMS and D2O in NMR spectroscopy. So TMS, it is the standard. D2O, it is a solvent. TMS is the standard, meaning that it's a reference compound. So D2O, it is a solvent. Signal of OH and NH disappears every time there is, for example, benzoic acid. Benzoic acid. The signal disappears for it. So therefore, we know that OH group is present. It's for identification of OH and NH group. So next, the B. The three isomeric ketones with molecular formula C6H10 are these. Complete table 7.1 to show the number of peaks observed in the proton 1H and M spectrum in the carbon 13 NMR spectrum for each compound listed. So first thing you would have to do is draw each of these ketone compounds, like I've drawn here, where this first one, pentan 2-on. Pentan is 5 carbon, 1, 2, 3, 4, 5. Double bond in a ketone in carbon number 2. So number of peaks observed in the proton NMR spectrum means that how many different carbon atoms that have different environments. This is number of proton, this is number of carbon. So carbon, 1, 2, 3, 4, 5. 5 different environments, 5. For H, there is 4. 1, 2, 3, 4, because there's no H atom here. So 4. Pentan 3 on, 3 1. So 1, 2, 3, 4, 5 at the 1 O. So number of peaks observed in the carbon 13 NMR spectrum. There are 1, 2, 3 different kinds of carbon atoms with 3 different environments, and therefore there's a 3 here. Number of peaks observed in the proton. Proton focuses on H, remember. This focus on C. H atom, meanwhile, this does not have an H atom. It is out. The H atom environment in here and in here is the same because it's symmetrical, and therefore this H atom has the same environment as this H atom, and therefore there's only 2 different peaks observed. 2. 3-methyl butanone. But is met at prop but, so there are 4 carbon atoms, so met at prop but with 3-methyl on 3-methyl on carbon number 3. There is a methyl group, and a ketone, there's no way ketone is at the ends because that forms an aldehyde. So ketone is in the middle. The only choice in the middle is either here or here, but this has 1H here, and therefore it cannot be occupied by a double bond O. 1, 2, 3, 4. The carbon has maxed out its number of bonds. Therefore, the number of peaks observed by the carbon is actually 1, 2, oh, you would assume that there are 5 actually. I almost got it mixed up. But then there are actually only 4 different carbon environments. Why? Because this is actually another metal group. So this is the same environment. So there are 1, 2, 3, and 4 different carbon environments, and therefore the answer is 4. For H atom, there are actually only one H atom. These all 3 H atoms have the same environment, therefore it's counted as 1. And there's no H atom here, and there's 1 H atom here, so this is second different environment. And the H atoms here and the H atoms here experience the same type of environment. Therefore, there are a total of 3 different environments for this 3-methyl butanone compound. So C, cortisone. Cortisone, this compound, is a naturally occurring chemical that contains chiral carbon atoms. Deduce the number of chiral carbon atoms of one molecule of cortisone. So we can count it here. Let's mark it with the star. So double bond has no chiral compound. Okay, so let's not mark that first. See, double bond O has no chiral compound. This one have 2 H atoms, so it's not a chiral compound. First chiral compound. Okay, has a HH. Second chiral, third chiral, fourth chiral, fifth chiral, HH, 6 chiral. And this is not a chiral because it's bonded to 2 metal groups, so CH3. 1, 2, 3, 4, 5, 6. There are a total of 6 chiral carbon atoms. So for CII, cortisone is reacted with an excess of NABH4, which is a reducing agent, and it reduces ketone. So all this double bond O is converted to bond OH. And state the molecular formula of the organic compound formed. So this is the molecular formula of cortisone, but then it is reduced, and so it will change to C21H34O5. And because this is already annotated with a pencil marks, this is actually supposed to be a pencil mark. It's not printed on paper, and so I'm going to use an example from the original question paper. So let's first form the OH. Form the OH. H, OH, H, O, OH, H. Now let's count how many C atoms first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. C21, H. 1, 2, because it's a double bond, only one here. And then this bond is already 1, 2, 3, 4. So the C atom already is bonded with 4 other bonds, so there's no more H atom. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and 32. But then this C atom is actually C2OH, to an R group, to H, to H. So there's 2 H's, 32, 33, 34. So H34, and then O. 1, 2, 3, 4, 5. So C21H34O5 as stated in the paper. C21H34O5. So correct. Cortisone is an optically active molecule. Explain what is meant by optically active. Optically active is a substance that is able to rotate the plane of polarized light in opposite direction, or rotate the plane of polarized light in clockwise direction and anti-clockwise direction. Okay, next. 8a. Compare the relative acidities of ethanol, ethanoic acid, and chloroethanoic acid and phenol. So chloroethanoic acid is just ethanoic acid with one of the H atoms interchanged with Cl. So the order would be chloroethanoic acid, phenol, and ethanol. So to understand what I've written here, it's easier to understand if I review this first. So why is chloroethanoic acid more acidic than ethanoic acid? So chloroethanoic acid is ethanoic, so two C atoms, C bonded to C, bonded to O, bonded to OH actually, bonded to HH, and with one of the H interchanged with a Cl atom. Meanwhile, CH3COOH is just CHHCOOH with all its H atoms. So it's pretty much the same, just the difference is with a Cl atom instead of a H atom. So the reason why every time there's a Cl atom or a halogen atom, it's more acidic always compared to its normal compound, because the halogen atom or chlorine acts as an electron withdrawing group, so it's more electronegative. It takes electrons, and so the O minus, so it takes electrons from here, it takes electrons. So the O minus is less negative now because there's less electrons in here. And so less negative means that it's more difficult for it to react with H plus ions, and therefore there's a high H plus ion concentration in the surroundings. So the OH bond weakens, higher H plus in surroundings, and so it's more acidic environment compared to ethanoic acid. Okay, next we have, that's for comparing chloroethanoic acid and ethanoic acid. Next, we're gonna focus on these three. Ethanoic acid is a carboxylic acid, phenol, and lastly is ethanol, which is an alcohol. So first, why is ethanoic acid the most acidic? Ethanoic acid, this structure is the most acidic because electrons from OH is withdrawn and drawn to the C double bond O. This is C double bond O. And so the carboxylate ion, which is this one, is stabilized by delocalized charge of electrons. So the delocalization spreads out the negative charge, and there becomes a less negative carboxylate ion. So it reacts with H plus ions less, and there is a higher tendency to form ions rather than forming this. So the equilibrium goes to the right, more H plus ions is formed, and more acidic environment. Higher tendency to form ions because dissociation will be more, and more compared to phenol, water, and ethanol. So this is the easiest one. The next one is why phenol is slightly acidic. Phenol is always slightly acidic because the lone pair of electrons in the O will overlap with the benzene ring or delocalizes the benzene ring, and so more distribution of electrons, making the structure more stable. This is favored. So equilibrium goes to the right, H plus atoms release, and the environment becomes more acidic. Lastly, why ethanol is the least acidic? So ethanol is the least acidic because it's an alkyl group, and the alkyl group donates electrons instead of withdrawing it. This one, withdrawing, donates, and so the CH3CH2O minus becomes unstable. In before examples, actually the ion is the one that becomes stable, but however in here it becomes unstable, so it is less favored. So it's because of electron accumulation, not spread out of electrons. So equilibrium shifts to the left, and less H plus ions are formed, and so it is slightly basic. So in simplification, you could say that the first carboxylate anion is stabilized. It is favored. It is favored for you could say for chloroethanoic acid. You could say this actually after saying that chloroethanoic acid is more acidic than ethanoic acid due to the electronegative or electron withdrawing effect of the Cl. So you could say that the carboxylate ion is more favored. And next, ethanoic acid is more acidic than phenol because the electronegative of the COH, electron withdrawing group of the COH. And next, you could say phenol is more acidic than ethanol due to the lone pair of oxygen overlapping or delocalizing in the benzene ring, making it more stable because more distribution of electrons and equilibrium goes to the right. Ethanol is weakest due to the alkyl group being electron donating rather than electron withdrawing. Okay, B. An excess of ethanedioic acid H, which is COOH but times 2, is reacted with warm acidified KMnO4. Say the type of reaction undergone by ethanoic acid. Describe what you would observe. It's actually ethanedioic acid. Describe what you would observe. Write an equation for this reaction. Your equation can use O or H if necessary. So the type of reaction that would occur is called oxidation because and there would be observation purple to colorless, color change. Because oxidation occurs, KMnO4 undergoes oxidation. And there's no way that with the use of KMnO4, reduction would occur because KMnO4 is an oxidizing agent. Let's write that. Oxidizing agent. Reducing another oxidizing agent is actually K2Cr2O7. Meanwhile, reducing agents are LiAlH4 and AbH4. Therefore, the equation is HOOCCOOH plus O forms 2CO2 and H2O when you balance it out. Okay, if you were to draw the structure though, it would be like this. Okay, for C, a section of a polyester is shown. Draw the structures of the two monomers that form this polyester. So this polyester is repeating. So it's repeating here and here is the same, and here is the same. So these are the two types, and then we write, usually if draw the structures for A2 level, we draw the skeletal formula. And so the first one is this, where I draw here. C is bonded to, this is actually OH, OH at first because it forms a ester bond, right? This is an ester bond. So CC bonded to OH, bonded to OH, double O, bonded to OH actually. H. Then later with another OH atom, this one taken, yes, out, and then an ester bond forms. And then for this, let's focus on the C atoms first. C to C, C to C, and then have a metal group CH3. You don't need to write this. And then after metal group bonded to OH, which is an alcohol, and then the double bond O bonded to OH, double bond O bonded to OH. Yes. Okay, D. Serine can polymerize to form two different types of condensation polymers, a polyester and a polypeptide. They're the structure of the polypeptide showing 2 repeating units. So the peptide linkage should be shown displayed. So peptide bond is NH2COO, C the 1O. So that is a peptide linkage. And so another serine will react with another serine and react with another. So in here we just need to draw 2 repeating units, which is like a form of dipeptide, you could say. So it's going to be C2C, C2C, and then bonded to actually it's not that. Actually it's C bonded to C, C bonded to C, which is bonded to, wait, I think I've made a mistake actually. It's supposed to not have C over here because it's supposed to be only C to C to C. So there should only be 3 carbon atoms in one monomer, which is 3, this one monomer, so only 3 carbon atoms. So C to C, C to C, and then bonded to CH2OH, CH2OH, and then bonded to double bond O, which this one, the OH will be gone, and the H atom from another, this is NH2, NH, and then this H atom of another serine molecule will bond with the OH of another serine molecule to form H2O as a byproduct, and a peptide bond will form between them. And then just need to draw the rest of the structure. So one H is out and then the OH is out. So we just draw this entire structure 2 times, which form this, and you just form bonds. Yes, and that's it. Make sure the peptide linkage is shown. Explain why condensation polymers normally biodegrade more readily than addition polymers. Because then addition polymers should actually see the proper question, what it states. Explain why condensation polymers normally biodegrade more readily than addition polymers. So it was my mistake that I have written it wrong. The actual answer is because addition polymers do not hydrolyze. Meanwhile, condensation polymers can hydrolyze, which is why condensation polymers can biodegrade more readily than addition polymers. Number 9. The structure of cyclohexane is shown in figure 9.1. So compare the relative basicities of ammonia, cyclohexane, and phenylamine. Explain your reasoning. So it's actually cyclohexylamine is more basic than ammonia, which is more basic than phenylamine. So basicity depends on the compound's ability to accept N. An alkyl cyclohexyl group are all electron donating but increases in electron density, which is increases in electron density, they have more electrons. So this is cyclohexylamine, this is ammonia, and this is phenylamine. So the lone pair from N in phenylamine, this lone pair actually delocalizes or overlaps the benzene ring, and this decreases the electron density, and therefore this has the lowest electron density and this has the highest electron density because they are electron donating. Okay, B. Cyclohexylamine reacts with ethanol chloride to form the corresponding amide L. So name the mechanism for the reaction shown in figure 9.2. So a reaction where it involves a compound or cyclohexylamine with ethanol chloride, which is an acyl chloride, will obviously be addition-elimination reaction. So for BII, complete the mechanism of the reaction between cyclohexylamine and CH3COCl, which is an acyl chloride. RNH2 is used to represent cyclohexylamine, where it is bonded to benzene. NH2 not benzene, it's cyclic. so it's not actually a benzene. So include all relevant lone pair of electrons, curly arrows, charges, and partial charges. So in here, the acyl chloride would actually be attacked by a nucleophile, NH2 double bond, and causes it to become dipole. And so this causes the double bond to break and causes there to be a lone pair of electrons in the O atom, which is negative, have received pair of electrons from the double bond, and so the lone pair of electrons move to the bond and form a double bond again later. But then the electron, because Cl is an electron withdrawing group, it moves there, and so because the lone pair have attacked the carbon atom, it has formed a bond, and therefore it is an N plus atom, central ion, and is bonded to R group, bonded to H2. Okay, then the reaction between cyclohexylamine and an excess of CH3COCl forms compound. This is actually M, forms compound M, and compound M has a molecular formula of C10H17NO2, suggest and draw the structure of M. So at first in here, cyclohexylamine reacts with ethanoyl chloride, which is an acyl chloride. So this plus this, one of the H substituted and form this. So one H left. The H, because there's an excess of CH3COCl, CH3COCl can react again with L to form M. And so the other H is substituted to form the same thing of here. This group copied to the other side. And so this is formed, and it is cyclic, not a benzene. Remember that this is cyclic. And as I've written here, H is substituted again from the NH. And that's it for this video. Thank you for watching.